Today is going to be a bit more abstract. I want to take a look at graphs and breadth first search. A graph is just a collection of nodes and edges. An edge is just an arrow between two nodes. And let's imagine this graph represents a street network and we want to get some food delivered, and the delivery person starts at location S. Like this is the address of a store and your home address is at E. Now we'd like to have some sort of algorithm to tell the delivery person how to get to us in the quickest way possible. Otherwise the food's going to be cold and maybe he won't just arrive today either. So one of the basic search algorithms in graphs is the breadth first search. And the way it works is it looks at always increasing circles around the starting point. So we are going to start in S, then take a look at 2 and 5. If we don't find the end here, we're going to take then at 3 and 9, because it's the next furthest away points. If we can't find it in that, we're going to take a look at 4, 7, 10, 13, and so on until we find our target location. While we do that, we also remember the path we took there, and that will be then the resulting answer. Here's a visualization of how that would look if we start in S. Quick explanation of the legend. The blue line outline means this is the start location. A red outline means this is the end location. Gray is we don't know anything about those nodes. Turquoise, blue, greenish is the color, is the node we are currently investigating. Q is the current nodes in question. That is the circle I talked about. And dark gray are the nodes we are done with. We know it's not there. We are not getting any closer. Over here are also some values, just the current node we're looking at, which nodes are queued up, that is the circle, the path we took to get there, and then the node that we actually found, that is marked with the label E. And as we step through this, we'll be adding the surrounding children of the node we're looking at. So if we step further in, we see we marked 3 now as queued. So we added to our circle, our range of search, the third node. And now we're looking at the next in the queue, which was a 5. On the next step, we're going to take a look at 3. And add 9 to the queue. And the next step is going to be a 9, and 4 and 7 will be under investigation. And if we step through this, eventually we'll find our E, and we'll see also the path we took here. That is going to be the shortest path, assuming that every street has the same length. Now, in reality, that's not the case, and there are algorithms to deal with that. We'll take a look at them some other time. For now, this is the base algorithm that pretty much all other algorithms are built on. And let's take a look at the code, which is not here. Right, so as I said, let's take a look at our data structure first. We're going to be working on graphs. A graph is a collection of nodes and a collection of edges. A node is just a name and some associated data. A name, I mean an ID. And an edge is a association of two nodes using their IDs. If we take a look at the actual search algorithm, we are going to have the graph we're searching, some method of recognizing the start nodes, and some method of recognizing the end nodes. Now this is a bit more general. This is if we start from, like, this also allows us to start at multiple nodes or look for multiple ends. Like, let's say you want to get delivered food from any of the locations or to any of the addresses. We initialize our queue. This is the circle we're looking for with the start nodes. And we can ignore this history. This is just for the rendering. And then as long as there's still unexplored nodes that we can reach, we're going to take a look at the next node. Mark this node as done. We're not investigating this node anymore. We need this to prevent going in circles. Like, if we imagine we're in this node, we add 2 to the queue, then we investigate 2, and then we add S back and bounce back and forth, and we wouldn't find anything. So that's why we mark it off as done. Annotation is just a simple object that has a value marking in it, and I've got some helper functions to actually mark things for us. It's immutable code again for the history. This could be perfectly mutable code as well. Right. Back to the actual code. So while the queue is not empty, we are going to take a look at the current ones. We are going to remove that one from the we are going to change its marking to done so that we don't revisit it. And then if that node is the one we're looking for, we are done. We're just going to return the current node and the path to it, which is in the annotation. We're going to see that in a second. If that's not the case, then we're going to take a look at the neighbors. And for each neighbor, we're going to check, is that neighbor still unexplored? If that neighbor is unexplored, we add them to the queue and mark them as queued as well. This is, again, just for the visualization. The important part is the queue part here. If we're done with the loop and haven't ever found anything, then we just return null with the history, because there was no node to be found. Of interest are the functions getNeighbor and markedQueue. GetNeighbors just looks through the graph's edges, and any edge that leaves the current node, we're going to look fetch the node this edge is pointing to. So graph.nodes.find finds that one. We know that they're always there because any graph that has edges pointing to non-existent nodes shouldn't be a graph in the first. That's not a valid edge in a graph. Marking done just sets the marking flag on the current one to done. Mark queued is a bit more interesting. It also assembles this path that I was talking about. That just takes the that adds the path of the node we came from. So this is the node we are going to, and this is the node we came from. So it takes the path of the current node as the from and adds the target node to the to this path, and this path is a recursive structure. So this here is again a path. It's defined here. A path is either a node, not existent, or a nested path, which is just a which contains a node that is the current node on the path and the predecessor. Right, and that's the entire algorithm. And